Welcome to this next lecture. Now that we have explored data and energy systems and learned about machine learning workflows, we are ready to bring these ideas together in the context of a real and highly critical task: the power system security assessment. Security assessment refers to determining whether the system can withstand disturbances without cascading into instability or blackouts. Machine learning can support system operators by predicting such risks quickly, even in highly complex and dynamic conditions. This lecture has two main learning objectives. The learning objective number one is to describe an example of how machine learning can predict power system security. And the learning objective two is to describe the main challenges and opportunities when applying machine learning to security assessment. So by the end of this lecture, you will see how machine learning can augment conventional simulation-based analysis and why this topic is gaining considerable importance. We begin with a striking reminder of what is at stake. The images on this slide show Houston in Texas before and during the 2021 power crisis. On the 7th of February 2021, the city is brightly lit up. By the 16th of February, vast areas appear dark, representing the widespread outages affecting millions of people. The economic damages were estimated at $195 billion, and the system was reported to be seconds away from a complete statewide blackout. This event illustrates how fragile the power systems can become under stress, and why system operators need fast, reliable tools to assess the system's security, tools that can identify dangerous situations before it is too late. Let us look at what a security assessment aims to determine. The two plots on this slide show frequency trajectories following a disturbance. In the upper plot, the system recovers frequency, dips briefly below 50 Hz, but stabilizes. This situation is labeled as secure, or y equals to 0. In the lower plot, frequency continues to deteriorate, dropping further below 49 Hz and failing to recover. This is an insecure situation, represented as y equal to 1. In practice, once a possible insecure situation is detected, operators can take preventive control actions, adjusting active and reactive power, denoted here as P and Q. The challenge is that detecting these situations ahead of time requires analyzing enormous amounts of data and running many simulations. This is where machine learning can offer substantial value. One of the main difficulties in security assessment is high dimensionality. The plot on this slide illustrates how active power injections vary throughout the day, with forecasts branching into a wide range of possible trajectories. At any point in time, many variables, dozens or even hundreds, affect system stability. The small diagram on the right emphasizes this point. Even with only two variables, and the system occupies a scattered landscape. With more variables, the space becomes vastly larger. So conventional simulation-based methods become computationally intensive under such complexity. Machine learning provides a way to map this high-dimensional input space to simple outputs, secure or insecure. And now we connect the idea of security assessment with supervised learning. The diagram on the left shows how time domain simulations can label system states. Y equal to 0 stands for secure, and y equal to 1 stands for insecure. These labeled examples become the training set for a machine learning classifier. On the right, you see the classifier acting on the same input space, given features such as the active power injections. This approach replaces thousands of heavy simulations with a fast-trained model that can classify states in milliseconds, the speed which is needed for near real-time security awareness. This slide illustrates how machine learning predictions integrate into SCADA environments. The model processes inputs, real-time measurements, forecasts, or derived features, and produces an output, such as alarm indicators. Below, the split between training data and test data highlights a familiar machine learning practice, ensuring that models generalize beyond the examples they were trained on. Embedding such machine learning models directly into the SCADA dashboards allows operators to view predictive alarms alongside traditional measurements and enhancing the situational awareness. Before returning to security assessment, the next slide uses wind generation forecasting to illustrate these machine learning input-output structures. The inputs may include the wind speed, the temperature, the time of the day, the month, and the table on the right shows how these variables are organized into a matrix, while the corresponding outputs, the wind power, form the target vector. The purpose of this example is to show how structured datasets for machine learning are built. The same principles apply in security assessment. Many variables form the input, while the security label, secure or insecure, forms the output. So let's return to the central example, predicting security, directly from power injections. The scatter plot shows how secure in blue and insecure in red operating points are as a function of two variables, which represent the active power generation at different locations. The task is to find a function that separates secure from insecure regions. So on the right, a map of the Dutch transmission system shows where these injections occur physically. Security is inherently spatial. Disturbances propagate differently depending on the location of the generators, of the loads and network topology. Machine learning helps approximate the complex boundaries between secure and insecure operating points and enable a rapid assessment without exhaustive simulation. So let us summarize. The 2021 Texas crisis illustrated the importance of a fast, accurate security assessment. Power systems can respond securely or insecurely, dependent on dynamic conditions. And in identifying those conditions is computationally challenging. And that is where machine learning can learn from time domain simulations to classify operating states very quickly. So the high dimensionality and system complexity make machine learning particularly suitable for this task. Once trained, machine learning models can support SCADA systems by providing predictive alarms and rapid assessments. As the grid becomes more dynamic, and due to renewable energy, weather variability, and new types of loads, machine learning-based tools offer powerful opportunities, but also new challenges, particularly regarding data quality, the interpretability of the methods, and the robustness. This concludes our introduction to machine learning-based security assessment.